All right, welcome to this video. In this installment, I'm going to talk about the speeds of molecules and therefore their kinetic energies. All right. Before we start on that, I've got a question for you to think about, and that question looks like this. It says, I have two containers, A and B. I'm going to move my head out of the way for a moment so you could read the question. Containers A and B are at the same temperature, and they both contain equal numbers of moles of argon gas. It asks how many of the following statements are true, and it gives you 4 statements down the list. The only information you really get from this is the picture, which makes it clear that container A is larger than container B. All right, so take a moment and think about that. This is not a totally simple question, so probably go ahead and pause if you want to actually give it some consideration. I'm going to just dig in and start reading through the statements and explain my way through them. The easiest one, I think, is the third one, which says the pressure in B is greater than the pressure in A. Right? I have the same number of moles at the same temperature. B is a smaller container, so it's got a smaller volume. Right, so that has to mean that B has a higher pressure. So let me get myself a pen and just check that one off, because that one's definitely true. All right. Up on the top of the list, I think I'll go there next, where it says the average kinetic energy is greater in A than it is in B. If you think about when we've talked about the kinetic energy of gas molecules, we've always said that it's set only by the temperature, really, right? It's 3/2 RT is the total translational kinetic energy. These are argon atoms, that's all they have. They're at the same temperature, so they have to have the same average kinetic energy. That one is out. Armed with that piece, I'm going to go down to the bottom, I think, which says the average force exerted on the wall when an argon atom collides with the wall is greater than in B than it is in A. Since the kinetic energies, it says the average kinetic energies are the same, and the masses are the same because they're both argon, that means the average speeds have to be the same. And if the speeds are the same and the masses are the same, then when it hits the wall, it has to exert the same amount of force, right? So that's got to be false. They can't actually have that be true. If the force per collision is the same and yet the pressure is higher in B, then it has to be true that there are more collisions in B than in A. So I'm going to check that one off. The easiest argument in favor of that second point is just that they're going at the same speed, and B is a smaller box, so you'll go back and forth across box B or cylinder B more often than you do across A. All of that means that my answer for that question is 2, so hopefully you maybe can agree with that. All right, let's now move on to talk about our speeds, okay? So I'm going to have a mole of gas, molecular weight is capital M, and the molecules in that gas have a mean square speed given by the symbol there that we've been using, which is just V squared with the bar over it, okay? The kinetic energy of that gas is just 1/2 mv squared, where that's the big M for the molecular weight. That thing has to be equal to 3/2 RT, right? Big M and R are both molar quantities, so they're in agreement with one another. That works out. Take that equation and solve it for the average of the square of the speed, V squared with the bar, and you get 3 RT over M. Okay, take that and take the square root of it down here, and you get a quantity which is called the root mean square speed, or VRMS. That thing says, well, take that V squared with the bar, that's the average of V squared. That says take the speed of each molecule and square it, take the average of those squares, and now take the square root of it. That turns out not to be the same as the average speed, although it's a little bit sometimes hard to convince yourselves of that at first. We'll see some examples of that before this video is over, which hopefully will get you on board with that if you're not already. That says that root mean square speed is the square root of 3 RT over capital M, where that's the molar mass or the molecular weight. It's also equal to 3 KT over little m, where little m is the mass for one molecule, right? So R and big M both are molar quantities. Boltzmann's constant K and little m, those are both quantities for one molecule. We can do it either way, we just have to be consistent. Otherwise, we're going to get an answer that's off by a factor of Avogadro's number, and that, of course, would be a big error. All right, so that gives us root mean square speed, one way to characterize the speeds of molecules in a gas. What we really want to think about, though, is how are the speeds distributed, right? That says we know some stuff about the averages, that root mean square speed. That's still an average property because it comes from the average of v squared. We want to think about just how can I tell how many molecules have a particular speed? And to do that, we need to put together another example of a Boltzmann distribution. In this case, it's generally known as the Maxwell-Boltzmann distribution or Maxwell-Boltzmann speed distribution because both of those folks worked in the development of this, this set of equations we're going to put together here. But like we did when we were in chapter 5, we can say the fraction of molecules in any energy state is proportional to just e to the minus epsilon over kT, where epsilon is the energy, right? For kinetic energies, we know that my epsilon, my energy, is just going to be given by 1/2 mv squared, because that's the kinetic energy of a moving mass, right? So that says my distribution function says f of v dv, the quantity on the left-hand side, which we'll talk about and actually point out what that means in a second. That's equal to a times e to the minus mv squared over 2kt, and there's that dv again. What does all that stuff mean? A is a normalization constant. This thing is a distribution function. All of my molecules have to have some speed or another. Right? So if I integrate my distribution function over all the speeds, I'll be able to figure out what A is, because they have to sum to 1, just like when we normalized wave functions earlier in the semester. F of V is the fraction of the molecules that have speeds between some V and V plus dV, where dV is just my infinitesimal volume increment, right? So the way we're going to find the value of A is by saying that if we integrate f of v dv over all the possible speeds, meaning from 0 to infinity, then we're going to end up getting a value for that that has to be equal to 1, because all the molecules have to have one speed or another, okay? All right, let's start to see how that's going to go. I know I just said I was going to integrate from 0 to infinity, and right as I said that, I realized that was wrong, because the first thing I want to do is to take this thing and think about it as one-dimensional, okay? So I'm going to take the distribution of speeds in one dimension, and that says that I could have a positive or negative speed. If I'm just going back and forth across something, right, I have to allow for the fact that I'm either going from left to right or from right to left, okay? If I take that situation, I want to do the integral then from minus infinity to plus infinity. I want to take this expression that's up here. My A is my normalization constant. That's what I'm trying to find. And I just put my e to the minus mv x squared up there and so on. When I do that, I get this integral. In order to evaluate that integral, the easy substitution to make is this one, which says if I just take this quantity here, mvx squared over 2kt, and call that x squared, then I can figure out what dvx is, and I get this collection of the constants times dx, all right? I'm going to use that to take my integral and rewrite it out of being this way to being integrating over x's. When I do that, I get the result down here, right? So my integral is still equal to 1. It's equal to a. If I take this thing here, my dvx, which is in here, that's getting replaced with this piece, right? So that gives me the part in front, which is not a function of x. So I take that out here with the a. And now I have my integral go from still minus infinity to infinity, but it's now just the integral of e to the minus x squared dx, okay? That thing is a standard form and can be evaluated, and if I do that, the integral itself is just the square root of pi, and so when I put that in there, I get this expression, which says that 1 is equal to this term over there. Solve that for a, and I get what's down here, that this says a has to be equal to this collection of constants, okay? So that gives me the Maxwell-Boltzmann distribution of speeds for a gas in one dimension, okay? And it looks like that. This is just a Gaussian distribution, right? And so because of that, the most probable speed is 0. Positive and negative speeds are equally likely. I have here a little bit of a Excel sheet, which if I flip through a bunch of stuff on my computer, we can play with a little bit to just see what's happening. That is not being shared, is it? No, I have to go in Zoom to do this, don't I? Not there. Hang on. I'm getting back to this. I really am. New share. Let's try this, and let's share this one. All right, now I've got my spreadsheet going here. Sorry, I'm still a little bit new at this. But if you check this out, you'll see that it says what? It says that I've got my graph, which tells me that up here, right now, I've got it set for the molecular weight is at 28, so this is, say, nitrogen. The temperature is at 300 Kelvin. Ignore the numbers, that's just where I've put in the formulas that figure all that stuff out. You can see the maximum is at 0 speed. In this case, my speeds are in meters per second. And I've got significant numbers of molecules out towards about 1,000 meters per second moving in either direction. Let's just see a little bit what happens if I play with this. Suppose I go from nitrogen, suppose I make it be, what, 40, that's argon. So we'll do argon. It gets a little bit more tightly peaked if I do that. If I take the temperature, instead of 300 Kelvin, suppose I make it 100 Kelvin. If I do that, my peak gets taller. In fact, it goes off the scale that I've got my graph locked on, unfortunately. So let me try 200. At 200, I come back on scale, but it's narrower. If I raise the temperature and make it 500, I'll get something that just has a broader spread of speeds. You'll notice as this happens, the height is changing as well. Again, that's because we defined that set of constants in front of the function so that the area under that curve is supposed to always be equal to 1, right? So if it gets taller, it's got to get narrower in order to accomplish that. If it gets shorter, it's got to get broader for that to work out. Okay, so that shows us a little bit about how that varies, and it should make sort of I don't know, essentially intuitively we should be able to think like it makes sense that the speeds on either side going in one direction or the other should be equally likely. All right, now we're at the part where I have to figure out how to get myself back to here, because although I'm back in the right place, I believe you're not there yet. So let me do this. All right, so now we're back in the slides, I hope. I'll be disappointed if I look at the file later and find out that didn't all work, but that's okay. So that tells us we know what this thing looks like, and putting that spreadsheet together really was just a matter of taking this equation and shoving it in there. So it just means loading up all the constants and getting things to work, okay? Now we want to start to work towards a three-dimensional gas, because after all, that's what we have in actuality. We have gases where molecules can move in any direction, x, y, and z. The first thing to say is there's nothing special about the x direction, right? So whatever was happening in the x direction should also be happening in the y and z directions. From that, we can start to put together a three-dimensional version of this distribution function. So I start down here and I say, I've got I take the terms for each of my velocities, my velocity components, and I take a dvx, dvy, dvz. If I do that, because each one of these three things here, f of vx, f of vy, f of vz, those should all be the same. So that just says take that thing and cube it. That gives me the piece in front of here looking like this, right? I stack up my volume elements over there, and they all look like this because, well, the average of Vx squared is the same as the average of Vy squared and same as the average of Vz squared. We used that idea in the previous video, I believe, for something as well, okay? In order to be able to get what this function looks like, the thing that's a little bit complicated is we have this volume element out here, right? Because I've got my three dimensions here. And so I have to think about what is the right volume element to use when we do this. This is similar to something that happened, when we integrated wave functions and had to integrate over r and theta and phi. We had to figure out what was the right volume element to get to count everything the right number of times. And that's what we're going to work on now, is just how to do that in this case. I want to start with a two-dimensional case because it's a lot easier to visualize. Essentially, in my two-dimensional thing, I get to have a picture here where the picture involves circles, right? If I made a three-dimensional case, my picture would want to be concentric spheres. And of course, there's no easy way to draw a diagram that represents a set of concentric spheres and be able to see what's happening in it, all right? So in my diagram over there, it's in a little bit of a strange sort of space, right? My axes are labeled Vx for the horizontal axis, Vy for the vertical axis. So I'm in a Vx and Vy plane, all right? Where those are just the x and y components of this velocity in my two-dimensional system, okay? In that plane, all the molecules that are moving at the same speed are on a circle. Okay, so if I picked some speed, if I'm along the axis, I can say up here that Vy is equal to whatever value that is, and Vx is 0, so that is the speed, right? Similarly, on this axis, if I'm in between, then I've got both x and y components, and so my speed anywhere on that circle is still the same. The diagram at least attempts to represent equally spaced circles, okay? So if the radius of the innermost circle is just delta V, then the radius of the next circle out is 2 delta V and 3 and so on as we go out there, okay? In each ring, just like that green shaded one, if we want to pick one, we can say that in that ring, there are molecules that have speeds that are in some range where the width of the range is delta V. Right? So it goes from some speed to that speed plus delta V. That's all the molecules that are in one ring. Because the circles get bigger as I go out, right? So that says that there are more molecules in those outer circles, relatively speaking, than their speeds would imply, just because there's more ways to get to that speed, more combinations of Vx and Vy that will get you to that speed. Right? Again, that's very similar to what happened when we averaged radial wave functions, right? And we normalized them. We had to put in like a 4 pi r squared piece in the volume element to account for that, where that was the area of a spherical shell. Something a lot like that is going to happen here in a moment, okay? So that's the idea that we need in order to do this. If I go back to 3 dimensions, my rings, my circles become spherical shells, okay? When I do that, very much like happened when we did that radial wave function idea, the volume element we need turns out to be 4 pi v squared dv, okay? 4 pi v squared is the surface area of a spherical shell in that coordinate system that has speed v, right? Again, in the 3-dimensional case, my coordinate system would be axes that were Vx, Vy, and Vz. And if I was anywhere on the surface of a sphere in there, I'd have the same actual total velocity for my molecule, all right? So that's what I'm gonna put in for the volume element in the distribution function, and that's gonna get me the expression that is now on the lower equation here. So this is where we left it before. Right? We had the idea that my 3-dimensional velocity distribution should look like this. Now I'm replacing this volume element down there with this one, where instead of being in terms of the components, it is now in terms of the total velocity of the molecule, right? That equation right there is the Maxwell-Boltzmann distribution function for molecular speeds. Right? In general chemistry books, we often show graphs of what that distribution function looks like and talk about how the average speeds behave and things like that. In a lot of Gen Chem books, they don't always actually hit you with that equation because it's a little bit more intimidating looking than a lot of the equations in a Gen Chem book. From a math point of view, but for our purposes, it's certainly not more complicated than a lot of other equations that we have encountered as we work our way through things, okay? So let's think about what that function should look like. That's the equation, right? We want to think about the parts that are functions of V, because a lot of stuff in there is just constants, right? I've got M is the mass of a molecule, KB is Boltzmann's constant, T is the temperature, which is just going to be a parameter once I set it for something. I've got a couple of pi's and some actual numbers, right? It's a function of the speed, after all. That's what we want to look at. And so we want to identify the places where the speed is. And those are, over here, I've got a V squared, right? And here, I've got an e to the minus mv squared, right? So those are my two terms. So what's happening to those terms? V squared is going up, right? If I raise v squared goes up and goes up sharply. E to the minus mv squared, on the other hand, starts at its maximum value at v equals 0 and goes down. Take those two functions and multiply them together, and what we're going to get is something that goes through a maximum, right? So there's a most probable speed or velocity, which corresponds to the point where my distribution function has its largest value. It's at a peak, all right? So let's actually go back to the spreadsheet, because I've got a 3-dimensional version in there as well that we can use to help us see what some of these will look like. So if I come back here and share you that screen, I click to the 3D tab, and now what I've got is similarly as before, it's still just this plot of the speed distribution. Now it's for the three-dimensional function. And so now it's really a distribution of speeds rather than velocities. We kind of change that up as we move between them. Because of that, there's a minimum now. My minimum value for the speed, of course, is 0. My molecule can stop, but it can't have a negative speed, right? And in principle, my speed could go out in this direction to infinite values. My speeds are plotted in meters per second. On the y-axis, I've got this just the distribution function quantity, the f of v. Right. I always like to explain these plots by saying they're actually similar in concept to the graph that I usually show after an exam that says, okay, this is the distribution of scores, and it says in this little bin of scores between, say, 80 and 85, there were this percentage of the total class. Right, that's a lot what this does. It says in some range of speeds that I might define, there's this fraction of all the molecules. Right now, my equations are set so that the molecular weight right now is set to 40. So let's say this is argon again, right? I'm at 300 Kelvin, so around room temperature. If I look at this, the first thing that's easy to pick off is I can see that the top of the peak, that's the most probable speed. That's somewhere probably around 400 meters per second. There's actually a part here that calculates it that says it's 353 meters per second is where that top of the peak is right there. So I actually didn't guess very well at picking where the top is. It talks about a couple other things that we'll meet momentarily. The average speed, which is a little bit higher than the most probable speed. The reason for that is this curve is actually asymmetric. We'll see that better in a minute, but it stretches out a little further on the high speed side than it does on the low speed side. You can see that by the fact that it doesn't get down close to 0 until I get out past 1,000 meters per second, even though the top of the mountain here is around 350, right? So it's kind of stretched out on the high speed side. That raises the average. The root mean square speed, that one that we get by taking the square root of the average of v squared, that's even higher. That one says it's 432 meters per second, okay? So that's the fastest of those 3 characteristic speeds, and we'll derive equations for all of those in a moment. Suppose I changed let's change the temperature first. Suppose instead of 300 Kelvin, suppose I went down to 200 Kelvin. That might go off scale. Yeah, it's going to go off scale a little bit there. So let's actually do something different. Let's change the mass down. Let's try nitrogen. And okay, so here's nitrogen at 200 Kelvin. I've got a most probable speed of 344. If I go to 300 Kelvin, we can see that my most probable speed goes up as it should. The hotter molecules will move faster, right? If I take my gas and instead of, we can compare if I flip it back to being argon for a minute, then we'll see that instead of 422 for the most probable speed for the nitrogen, at that temperature for argon, I go back to 353, right? And so as the molecules get heavier, they go slower. Lighter would make them faster. Hotter makes them faster. Colder makes them slower. Suppose I did something like make this be really light. Let's make it helium. If I do helium, I get something very different looking, right? So my most probable speed is up to what, 1,100 meters per second right now, okay? So that's something like 2/3 of a mile per second. That's a pretty good pace they're moving. My distribution is now very broad, right? So I've got a much wider range of speeds here for the light helium atoms than I did for my argon atoms. Okay, again, the area under this whole curve has to be the same. It's equal to 1. That's how we got the function. And that's why when it gets to be fatter or broader like this, it also gets a lot shorter. Okay, so that hopefully gives you some appreciation of how those different parameters would work. Let me actually switch myself back to the slides and see where we go from here. Okay. Oh, that's right. We're gonna figure out how we get the results that I used, the equations I used to put those blocks in the spreadsheet that we're calculating those, the average speed and what have you, okay? The most probable speed, that just says it's the maximum in that distribution function, right? So if I wanted to find the most probable speed, the way I would do that is just by taking the distribution function and setting the derivative of it equal to 0, okay? And so I forget if I did that one in the actual class stuff here or not, but we'll find out in a moment. If I want to find the average speed, what I do is I just say to get the average, I do it, it's kind of like doing expectation value stuff a little bit. What I do is I do the integral across all the possible speeds of the speed itself times that distribution function, right? It says, think about it, this is like if you wanted to find the average score on your exam. If I knew what fraction of the people made a given score and multiplied that by the score, do that for all the possible scores, that's how that would work out, right? That's exactly what this equation does down here. It says, I flipped there, didn't I? Yes, it says I take V times f of V, and I do that. Let me go back to the other slide. I apologize for skipping around. It does it without me trying sometimes. I get that my average speed is equal to this integral here, and to do that, I'm going to use a form that says that the integral, I've got to learn how to get to stop doing that. I promise I've been trying, but it's obviously not helping. I get one that says, use that standard form, x cubed e to the minus ax squared. I put in a, for a, I put in the m over 2kt piece for that. If I do that, then I can actually do the integral, and the result for the average speed turns out to be the version over here on the end is the one that we generally use, which says it's the square root of 8kt over pi m, all right? That's with K is Boltzmann's constant, M is the mass of an individual molecule. I could, if I wanted to, again, change those to R and to the capital M for the molar mass. That essentially just amounts to multiplying the top and the bottom both by Avogadro's number, and so it doesn't change the actual result any if I do that. If I wanted to find the mean square speed, the equation that we derived earlier, right? We would know we have to get the same thing. To do that, I would take my distribution function and multiply it by v squared and integrate that over all the speeds, right? When I do that, without doing the math all here, the result is the same as we got before, right? It's that the average of v squared is equal to 3kt over m, which again means that the root mean square speed is equal to the square root of that quantity, 3kt over m. All right, and so that tells me I can do any of those things as I want. And again, like I mentioned, if I wanted the most probable speed, I could get that by just taking the distribution function, setting the derivative of it equal to 0 and solving for that, because that's going to give me the maximum, of course, in the function, which is what we mean when we say we want the most probable speed. All of those things give me a plot like this, where in this one, I actually just have labeled the most probable, the average, and the RMS speed, right? I made this graph using actually the same spreadsheet I was just playing with. I just then drew the lines and the arrows in there to put them in the same place. Again, this version happens to be for argon at 300 Kelvin. If you compare the equations, at least for the average speed and the RMS speed, you can compare the constants in those, and that'll make it clear to you that the RMS speed is always a bit faster than the average speed. The average speed is always a bit faster than the most probable speed. The reason for that, again, is because this asymmetry in the function, the fact that it's got a tail coming out here to high speeds, that means that those faster moving molecules will influence the average and pull it higher than the most probable, and those faster moving molecules will even more influence the average of v squared, which is where VRMS comes from, so that moves even further, right? If these were going to all land at the same speed, that would mean that my distribution was symmetric. If I still had a Gaussian distribution, then all three of those things, of course, would be right on the peak of the distribution. That's not what we get for the actual three-dimensional speeds, okay? All right, in normal class time, this looks like it's another point where I had a question planned, and so this is a nice simple question. Gosh, this is actually probably a question that it wouldn't be horrible if I asked the freshman class sometime. So hopefully it's not too challenging. What's it say? Which of the following samples will have the highest average molecular speed? There's a little bit of work here to do here, actually. This is maybe a little bit more than I would have asked the freshman now that I look at it more. Go ahead and pause if you want to think about it. I'm going to just jump on and explain. The first point is that the pressures don't make any difference whatsoever, right? Because the average speed we just saw depends on what? It depends on the square root of t over m. That's the main thing, right? If we take those equations, just look at everything else that's in there, the square root of t over m is the part that actually is relevant to what we're doing here. As I look at these, I can see that the differences in temperature are relatively much smaller than the differences in mass, right? My masses are changing by a factor of 5 or 10 or 2 as I go across the different comparisons. My temperatures are changing. It looks like they're changing a lot, but I have to put them in Kelvin, remember? And so that says they go from 273 for the 0 degrees C1 to a maximum of 323 for the 50 degrees C1. So that's never as big of a change as any of the different mass changes are, right? That leads me to feel like the helium is going to have to be the one that wins out, even though it's the coldest, right? If I wanted to do this systematically, I guess I could start off by saying that one would be the most silly choice to pick, I guess, right? Because the B and C are both argon, and that's the colder ones. That one is definitely out. Of the others, if I take this one, the change, neon is only half as light as argon. That's a factor of 2 change. The argon is slightly warmer than the neon, but that means the neon's faster than the argon, and it's actually bound to be the helium down here that actually wins out. I didn't do the numbers, but I can tell just looking at it, that's got to be the one that is the fastest molecules, okay? I have one more thing to finish this up with, which is I'm an experimentalist, meaning I actually used to do science experiments and research, and so I always like to think about how do we know that thing is true, right? When Maxwell and Boltzmann actually put this distribution function together, they did it by essentially just doing math and physics. They said it just has to be this way. It turns out it's been a great many years now since we became able to measure this. So I wanted to mention that we actually, first of all, know for a fact this works. It's experimentally confirmable. And second, just talk a little bit about how would we know that? How would we measure it, right? So if you want to measure the speed distribution, what you want to do effectively is you want to have a race. In this case, we want to have a race between molecules, okay? That's not the easiest race to start up, but it's not all that hard. We, gosh, aren't doing it right now. We used to have an experiment in the PChem lab for the chem majors in which they actually would measure this stuff. So the way I do this is I start over here on this side, and I've got where it says gas source, that just says I've got a tube with a little tiny hole on the end of it, okay? So I take a thing and I put a tiny pinhole on there. I'm talking a hole on the order of, say, a few microns in diameter, okay? Inside that tube, I put some gas at a decently high pressure. Okay, the effect of that little pinhole is essentially to spray the gas molecules out of that hole, a bit like if you put your thumb on the end of a hose and just spray the water out, you get a jet of water going kind of forward. That's what's going to happen here, okay? All this stuff is under vacuum because I don't want my molecules to be crashing into each other once they get going downstream. Okay, so here, this little shaded area here, that represents just a puff of gas coming out of my tube, but it's mostly, it's got to be focused going in the left to right direction, because if the molecule wasn't going in this direction, it wouldn't have been able to go through the hole after all, right? So that comes to just a wall with a hole in it, and this is actually a fairly elaborate hole. It would be a small hole. Sometimes it would have a little conical thing to actually make sure it's picking out just a small sample from all the molecules. When I do that, on this side, that just gives me now a more defined, this is like a collimator essentially, right? It gives me just a defined direction in which the molecules are flying. So I've got this stream of gas going down, and it's going along a line through my vacuum chamber. Okay, I've got more vacuum pumps in all these places. The important part for purposes of getting the race going is the starter's gun, and that's what this spinning wheel is supposed to do, okay? And so here I've got this wheel, the little line there is meant to represent there'd be a slit cut into it. And I'm sorry, that wheel is going to now spin around at fairly high speed, and what's going to happen is the wheel is going to block the molecules most of the time. It's only when my narrow little slit comes by that it's going to let a tiny little slice of molecules get through. Right? So I represent that here by coming through another wall. I have this. If my wheel's going fast and that slit is narrow, then that's a very, very narrowly defined pulse of gas, right? So at that point, I have a bunch of molecules that have gone through that spinning wheel at the very same instant, because if they didn't go through it right then, they should have been blocked by the wheel, right? Next step says I have to let them go for a while. So I want to let them fly a pretty long distance. The distance from here to down here where I'm going to measure them, I'd probably want that to be like at least a meter or something like that, right? The longer I can make it, the better, because the further I make the race, the farther ahead the fast ones are going to get from the slow ones, okay? So by the time they get down here, you can see I've drawn that my pulse of gas has stretched out in time, right? Because the fast molecules are now on the front edge, the slow molecules are on the back edge. I put a detector down there. Something like a mass spectrometer would be good because it can just count how many molecules are getting there in a given instant of time. And if I do that, then I know how much time it took each little bit of gas to run the distance from my wheel to my detector. And out of that, I can measure their speeds, right? If I know how far you went and how long it took you, I can figure out how fast you were going, okay? Doing that, we find out that our molecules very much match the equations that Maxwell and Boltzmann put together. They got it right. There are some experiments, gosh, a long time ago, some of the earliest historical experiments that measured this were really elegant because they did it without having things like mass spectrometers that we have now. But it's nowadays a relatively straightforward experiment to do, okay? All right, that finishes out this video. I'll be back to record another one next time. Thanks.